Hello guys, welcome to our class today, Thursday, March 17th, 2022. As an announcement in the recording that next week we will have Wednesday and Thursday classes as regular. If we find that we need more time, then we will recover yesterday class by using the tutorial time, and I will send a separate link. We'll decide next Thursday. I'll send a separate Zoom link for the Friday class next week. Tomorrow you have in-person class for tutorial for assignment 2. If you have any question, the TA will answer it. If you have any difficulty in the assignment, and today we will continue from where we stopped last time. So here, consider the dilemma. If I have something, this is what we are gonna to see. If the Turing machine accept, then reject. If it's reject, then accept. This is the philosophy that we will work. Like the sky is blue. The sky is blue. This is slide here. The sky is blue. Is it true or false? The answer is false. 1 plus 1 equal 3. The answer is false. You will mark this question false. True or false. So, if we said the sky is blue and you said it true, this is totally false. If you said false and somebody think that the sky is blue, then he might accept your answer or reject your answer. The thing in Turing machine, we will see now, if it's accept, then reject. If it's reject, then accept. We will see how it's going. Universal Turing machines and simulation. A universal Turing machine, UTM, is a Turing machine that can simulate the behavior of any Turing machine on any input. For example, if we have a Turing machine called M, and we use the notation M between these signs to denote the description of M encodes as string. Additionally, we will use notation M, W to denote a string describing a Turing machine and an input string W. So here, when we see this is the Turing machine and the input will be a string called W. We can provide MW as input to universal Turing machine and design a universal Turing machine to simulate the execution of M on input W. Some aspect of universal Turing machine. U is a computer, so it's a computer. M is a program. W is the input argument. The description of U is independent of M. So the description of the computer is independent of M. M is a program that should be run in that computer using an input string W. This is the scenario. So, and description of U as if U was the cardinality of Q equal 2 states, either reject or accept. And the delta equal 6. Tape symbol are known. So we have 6 tape symbols. The precise details of U aren't considered here. All you needs to keep track of is what state M is currently. So the machine at what state, and what M's head is currently pointing at the memory in these 6 locations. Then at each step, it can scan through the description of M to decide what to do next. And you remember, we are moving left or right. If we are at the beginning of the tape, we have to move right. What does U, or what U does? What is the job of U? U works as follows. Given input MW, where M is a Turing machine and W is a string, simulate M on input W. If M accept, halt, and output accept. If M rejects, halt, and output reject. Notice that if M accept W, then you accept the combination of Turing machine and the input string. If M reject, then it will reject. If M loops on W, then U loops in MW. And you remember, we talk about three situations: halt and reject, halt and accept, or loop in the previous lectures. The language of U. What is the language of U? Using a Turing machine, and every Turing machine has a set of strings that it accepts. In another word, so if we are saying you recognizing language, so what language does you recognize? You remember when we talk about recognize and decidable, recognizable and decidable? It recognizes MW, the set of accepting Turing machine string combination. So we have a Turing machine and the string combination all together. So ATM will take the combination of M and W, TMM accept the string W. ATM is known as the acceptance problem. Clearly, U recognizes ATM. Notice, however, U does not decide ATM. It recognizes but not decide. And we talked about this before. If M loops on W, then U loops in MW. So still we are in definitions. Now, this is the important point, guys, which is ATM is undecidable. It is recognizable, but it's undecidable. Well, maybe there is some TMH that could check M and somehow decide if it would go into a loop on input W, and then could reject. Theorem, ATM is undecidable. Proof to follow. A decider for ATM. Let's begin by assuming the existence of a program H that decide ATM. H works as follows. Give on input MW, where M is the Turing machine and W is the input string. If M accept, halt and output accept, otherwise halt and output reject. Notice we define H as a decider. It always answers yes or no to question of whether machine M accept input W. So here, what is the difference? The difference here, if M loop, then loop. No halt. But here we assume if it's decidable, then it's either accept or reject. Even with loop, it will reject. So this is the difference. What is the Turing machine encoding? Define some Turing machine encoding scheme. All TMs now correspond to some string, and we can sort them alphabetically, then to produce some kind of canonical ordering of TMs. Now we can talk about the first TM, the 10th TM, however. So we'll put TMs in order. A table of all TM and their string encodings. Define the following table. Let row I correspond to the ith Turing machine. Mi, let column J correspond to the string encoding of Mi, like I, which is M1, M2, M0, M10, whatever. Run H on the table, the program. We call the program H. For each row Mi and each column Mj, run H on Mi and J. I will explain it also more clearly later with the class notes. Fill in the I and J with accept, otherwise fill in and reject. The diagonal of this table, all cells KK, which mean, you know, once we have a table, there is an index 0, 0, 1, 1, 2, 2, which correspond, the first digit is for row and the second digit for column. Once the diagonal of this matrix or table all cells KK for K greater or equal to 1 represent all Turing machine MK fit their own description MK as input. Some will accept, some will reject, some will loop. We can now define two sets. Those TM that will accept their own encoding and those that do not. So why we are doing this? There is a reason behind this. There is no special significance to feeding a TM its own description as input. No need like to give the description of a TM as an input. It's one of the the properties of this TM, or one of the description of this TM. Why I have to insert it as input? Except, what is the exception using this proof? Is helping us to achieve our contradiction. We need a contradiction. Running TM in their own description, consider the language of all TMs that do not accept their own encoding as input. This is at the beginning of the class, I told you, if it's accept, then reject. If it's reject, then accept. So MI does not accept input MI. This corresponds to all cells in the diagonal that are reject. Is there a Turing machine that can decide this language? Suppose the nth Turing machine, MN, can decide the language L. What is language MN accept? These are the questions that we have to ask ourselves about it. It's accept all strings MK where Turing machine MK accept input MK. Thus, MN can be described as follow. Given input string MI, run H on input MI, and as an input MI itself, if H output accept, halt, and output reject. Here this, I told you the philosophy, if it's accept, then we will reject. If it's output reject, then we will accept. Notice by contradiction, MN does two things. It runs MI on description and output the opposite of what H output. If H output the program accept, then we will reject. If it's reject, then we will accept. So MN and its own description. Consider now what happened when MN is run on its own description. Give the input string MN and all our description of MN we have to run H on input MN and MN itself. If H output accept, halt, and output reject. If H output reject, then halt and output accept. Recall H accept MN if MN would have accepted MN as an input. MN cannot exist. Why it cannot exist? We will see. Consider both cases of MN run on its input MN. Case 1, MN output accept. That means H output reject, meaning MN did not accept itself as an input. But this is the case where MN accepted itself as input by contradiction. Case 2, MN outputs reject. That means H output accept, meaning MN accepted itself as an input, but this is the case where M did accepted itself as an input, another contradiction. And this could not be done. Conclusion, MN cannot exist. That's why ATM is undecidable on itself. By way of logical paradox, we see MN cannot exist, but MN merely does the opposite of what H does. Therefore, by extension, H cannot exist, and since H decides ATM, therefore ATM is undecidable. I know it's not easy to understand it. If you focus with the class notes, that will be okay with you. Then we'll come to another problem that we call it the halting problem. Why the program is not halting, why the Turing machine is not halt and decide. This halting problem say, halting problem, if we have the Turing machine M and W as an input string, Turing machine M halts on a string W. The language halt consists of all Turing machine that halt. Either accept or reject a given input. There is a decision. Reject or accept. Can you decide this language? Can you always tell differences between TM stuck on a loop and one that just taking a really long time? This is the problem. I run a program, it takes long time. I don't know it's loop or halt, or still the computer or the Turing machine is computing and not done yet. So this is a big problem for people who work in computation. It is easy to see we are being able to decide this language would be useful. If you could decide ahead of time if a program was going to run forever, which means going in a loop, you wouldn't have to wait around forever to find out. So halt also is undecidable. Proof toward obtaining contradiction. Let's begin by assuming halt is decidable. So we will assume that halt is decidable, same as what we did before now. We assume that the universal Turing machine or ATM is decidable, then we found it's undecidable. The same thing we have to do with the halting problem. So we'll go, if M accept, then reject. Then we'll find that clearly T decide ATM, if accept, T accept, if M reject, T reject. If M gets stuck in a loop as decided by us, then T reject. What is the problem? If halt is decidable, then clearly ATM is decidable. But we prove that ATM is not decidable. But we already approved that ATM is undecidable. This contradicts our initial assumption that halt is decidable, so halt is not decidable problem. Why does the halting problem matter? For a few reasons. Guys, this slide is important for the final exam. It proves the existence of undecidable, uncomputable, problem establishment, a fundamental limit that what can be computed. In his seminal paper on computable numbers, if you need to read the paper, you just click on this. Turing reduced the halting problem to the, so there is a type here. Entscheiden problem, meaning if you could solve the later, you could solve the former. But since we proved that we cannot solve the former, then we cannot solve the later. This is his philosophy. As sort of byproduct of all of this, he invented the notation or the notion of the stored program computer. A Turing unrecognizable problem. Consider the complement of ATM. So ATM, this is the complement. MWTM does not accept string W, because the ATM, we said it accepts string W. The complement does not accept. We already showed that ATM was Turing recognizable. Simulate M on W using our universal machine. U and output accept if M output accept. But what about ATM complement? So ATM also is a Turing unrecognizable. ATM is undecidable, but recognizable. But since the ATM is recognizable, then the ATM complement is unrecognizable. Here they will do the same, run U and V in parallel on W. If you accept halt and output accept, if V accept halt and output reject. Let's consider what we have accomplished. W is a decider. It accepts U when accept, reject when V accept. We decide ATM, it accept when MW belong to ATM and reject when MW does not belong to ATM. But once again, ATM is undecidable. Therefore, we have reached contradiction somewhere, but where? We will know ATM is recognizable. Thus, our assumption that ATM is recognizable must be false by contradiction. Okay, guys, let's try to simplify the handout by using our class notes. So, what is the undecidability? Are there problems cannot be solved using TM? This is what we are trying to see. When I say undecidable, that means, is there any problem that it's not computable, cannot be solved by Turing machine, we will back to our previous handout, which is Church-Turing thesis. What Church-Turing thesis said anything can be computed by a TM, universal model of computation. So can we define a problem that is undecidable by ATM? Because Church-Turing that said anything can be computed by a Turing machine. So we will represent now a Turing machine, and we will see. A Turing machine can be represented by using a finite string consisting of symbol from some finite alphabet. And we know that before. Can be converted to a binary string using 0 and 1. So our alphabet will be 0 and 1. To every binary string, we can associate a unique number. Assume we have this number, 0010, or we have 00010. When convert to a decimal, both of them equal 2, because the zeros from the left doesn't matter how many zero I have. If we add a 1 at the left of zeros, are they the same? No, they will not be the same. So there will be 18 and 34. So it is different. So if I have a string 0010 and 00010, mathematically they are the same. But as a string, they are different. If I add 1 here and 1 here and I found them different, then they are different. To every natural number, we can associate a Turing machine. If a number does not map to a Turing machine by the aerial representation, then we map it to the Turing machine that accepts all inputs. So assume here we have the natural number, and here the set of all possible Turing machine. So some Turing machine can accept different natural numbers based on their description. So let MJ denote the jth TM, and let SJ be the jth binary string. So here, a non-Turing recognizable language. Let LD consist of SJ, SJ not belong to L of the Turing machine of MJ. Here we have a semi-finite table. We start from the left to the right. And for example, if we have an S1, it's accept, S2, it's reject, S3, it's accept, M2, reject, accept, reject, reject, accept, reject. So if it's accept, we'll give a 1. If it's reject, we'll put a 0 or loop. Add a string such SJ such that OJJ, which is the diagonal, equal to 0. Suppose LD is a Turing recognizable. So if it's Turing recognizable, then there is exist, this symbol means there is exist a Turing machine called MI such that LD equal L of I. Consider the following case. MI accept SI, then SI not belong to LD. SI not belong to L of M2. Then MI, just give me a sec to stop the watch. Sorry for that. Then MI does not accept SI. MI does not accept SI, SI, then SI belongs to LD, because by assumption here, guys, to make you, the assumption if SJ not belong to L of I. So if it's reject, then it's belong. So SI belong to LD, SI to L of I, then SI accept SI. So if it's reject, then accept. If it's accept, then reject. So LD is not a Turing recognizable. This is summarized the 3 slide, how we prove that it's Turing undecidable. An undecidable language, assume that we have ATM, MW. So here encoding of Turing machine M and the string W, M accept W. We will show that ATM is Turing recognizable. This is our assumption. Simple algorithm, input MW, simulate M on W. If M accept, then accept. And if M reject, then reject. We will see. Prove that ATM is undecidable. Suppose that ATM is decidable. Then there exists a halting Turing machine such that ATM equal L of H. So here we have MW, we enter it, yes or no. If yes, then M accept. If no, then does not accept, reject. Construct a Turing machine N as the following. Input M, simulate H on M of M, encoding of M. If H accept, then reject, else accept. So we're doing it like this one. Here, this guy's graph summarize the slide. The way of the proving the slide. So if I ask you to prove, then you can use these images in the exam. Or by writing, you have both choice. Now consider what happens if N is given the input N, encoding of itself as an input. N accept N, H does not accept N does not accept N. By contradiction, so ATM is undecidable. So this is easier than the handout, but you are free to use either of them. Note that N is also a halting TM, since H is a halting Turing machine. What does that mean? We have a Turing machine is undecidable, a Turing machine is Turing recognizable, then ATM is not a Turing recognizable. ATM complement. Since this is Turing recognizable, then should be not. So M and MW does not accept W. Proof. If L is undecidable and L is a Turing recognizable, then the complement of L is not a Turing recognizable. As simple as that. So here we back to our graph in chapter 4, I don't know, or 5. So here we have the finite automata and regular language, the context-free grammar, then the decidable language, then at the upper level, which is the complement, which is Turing recognizable, and a Turing recognizable, which is ATM. Okay? And we call this Chomsky hierarchy. Chomsky hierarchy. So co-TR, co-Turing recognizable, L, that means L complement is a Turing recognizable. This is what we call by that. So halting Turing machine, MWM halt on W, we will show that HTM is undecidable using the fact that ATM is undecidable. So assume HTM is decidable. So there exists a halting Turing machine N such that HTM equal L of that Turing machine N. So HTM is accept the L of N. The goal, can we have a machine as H? So construct a halting Turing machine for ATM using N input in MW, simulate N on MW, N is a hardwired into this H. If N reject, then reject. If N accept, then accept, simulate M on NW. If M accept W, then accept, else reject. Halts because N is halting Turing machine, and H simulate M on W, step 3 here. If M halts on W. So look at the correctness. M accept W, H accept MW. M does not accept W, then loops or reject. If it's loop, reject and back to step 2. If it's reject, then reject and back to step 4 here. Then H is a halting Turing machine for ATM by contradiction. HTM is undecidable. Also, we can show the same as H is a Turing recognizable. I know these proofs are a headache. You can see in the book also with more explanation. The main idea that I need you to know that H is a Turing recognizable, ATM is a Turing recognizable, ATM is not a Turing decidable, H is not a Turing decidable. These are the main thing I need, and to understand the simple proof by graphical, by writing as much as you can. Any question till here? Questions? Okay, if you don't have a question, so let me back to the course. So next week, we still have 3 handouts, but they are related. So we will start talking about computational complexity, the class P and the class NP. So we'll start talking about the running time, the big O notation, next class. On Wednesday, then we'll go to handout 11, which is NP complete and the $1 million question, does P equal NP? We'll talk about those complexity issues. And we'll prove something hard and soft. And handout 12, which is the last handout, the NP hard and BPP. We'll talk about those. If we can finish on Wednesday and Thursday, that would be great. If we cannot, then we will use some time of Friday, as I mentioned before. Next week. If you don't have any question, feel free to leave. If you have any question, don't hesitate to ask. Thank you, guys. Yes, next class is Wednesday, Brandon. Yeah, regular. Yeah. Thank you, Mahira. Thank you, Brandon. Okay, see you. Bye.